Assalamualaikum. My name is Sunil Zara, registration number 21TE103. I am here to present upon the topic adaptive filters and an application. In this topic, I will discuss about what is adaptive filters, what are key components of adaptive filters, the basic block diagram, what are the common algorithms that are used in adaptive filters, and at last we will discuss about the applications of adaptive filters. Now moving towards that, what is an adaptive filter? An adaptive filter is a digital filter that has a self-adjusting characteristic. It is capable of adjusting its filter coefficient automatically to adapt the input signal via an adaptive algorithms. An adaptive filter adjusts its parameter automatically based on the input signal and a desired output signal to minimize a predefined error functional, usually by the mean of square error. Unlike static filters, adaptive filters continuously modify their behavior to respond to the change in the signal environment. Key components of adaptive filters. Adaptive filters have three major key components: filter structure, adaptive algorithms, error signals. In filter structures, common structure include finite impulse response and infinite impulse response. And in adaptive algorithms, there are the core of adaptive filters that updates the filter coefficients. Popularly, there are three major algorithms: least mean square, recursive least square, and Kalman filter. And at last, error signal, the difference between the desired signal and the actual output of the filters. Now moving toward the block diagram, here is the major block diagram of adaptive filters. This block diagram will show that how noise is cancelled by using the adaptive filters. So this block diagram shows us a noise canceller. The DSP system consists of two analog to digital conversion channels. The first, microphone with ADC, is used to capture the desired speech, S of n. However, due to a noisy environment, the signal is contaminated and analog to digital converter channel produce a signal with the noise. That is, D of n is equals to S of n plus N of n. The second microphone is placed where only noise is picked up, and second analog to digital converter channel capture noise X of n, which is fed to the adaptive filter. The noise signal X of n from the second channel is correlated to corrupting noise N of n in the first channel, since both come from the same noise source. Similarly, the noise signal X of n is not correlated to the desired speech signal S of n. The adaptive filters contain a digital filter with adjustable coefficients and the LMS algorithm to modify the values of coefficients for filtering each samples. The adaptive filters contains a digital filter with adjustable coefficients and the LMS algorithm to modify the value of coefficient for filtering each samples. The adaptive filter then produces an estimate of noise Y of n, which will be subtracted from the corrupted signal, that is D of n is equals to S of n plus N of n. When the noise estimate Y of n is equal or approximately near to the noise N of n in the corrupted signal, that is Y of n is nearly equal to N of n, the error signal is produced, that is E of n is equals to S of n plus N of n minus Y of n nearly equal to S head of n. Approximate the clean speech signal S of n. So here the noise is cancelled. Now common adaptive algorithms. We have discussed that there are three main algorithms: least mean square, recursive least squares, and Kalman filter. In least mean squares that are used in simply and computationally efficient update filter coefficient using the gradient descent approach, used in application requiring real-time processing due to its low computational complexity. Second, recursive least squares. They provide faster convergence and better performance than LMS. They are more computationally and intensive. They are suitable for applications where rapid adaptation to changing environmental is critical. In Kalman filters, optimal for linear system with Gaussian lines, and they are widely used in tracking and navigation systems. Now moving toward the application of adaptive filters. Adaptive filters have various applications in telecom industry. Here are some few applications that are noise cancellation, echo cancellation, adaptive equalization, system identification, and beamforming. So, what is noise cancellation? Adaptive filter can effectively eliminate unwanted noise from the signals. This can be widely used in speech enhancement, hiring ads, medical devices, and speech enhancement, reducing the background noise in voice communication, filtering out amendment noise to improve the clarity of the desired sound that are used in the hearing aids. In medical devices, they are used for removing electrical interference in ECG and EEG signals. Echo cancellation. In telecommunication, adaptive filters are used to cancel echoes that are reflected to the source, improving the clarity of the conservation. This is essential in telephone networks and voice over internet protocol. Adaptive equalization use this is used in communication systems to correct the effects of signal distortion caused by the transmission mediums. They are mostly important in modems and wireless communication systems. System identification. Adaptive filters can model or identify the characteristics of unknown system by analyzing its input and output systems. System identification applications includes in control system and signal predictions. In control system, adapting to changes in the system's dynamic for optimal performances, and in signal prediction, predicting future value of the signal based upon the past data. And the last application is beamforming. In antenna array, adaptive filters are used to direct the beamform pattern of antenna array towards a desired signal with suppressing interference from other directions. They can be used in radar systems and smart antennas. In radar system, enhancing the target detection and tracking, and in smart antennas, improving the signal quality in wireless communication system. At the last, I will sum up my discussion. So, adaptive filters play a pivotal role in the variety of fields by providing robust solution to signal processing challenges. Their ability to adapt in real time makes them indispensable in environments where signal characteristics are dynamic and unpredictable. Whether it's enhancing audio quality, improving communication system, or processing biomedical signal, adaptive filters continue to evolve and find new applications, driving by advancement in algorithm developments and computational power. Thank you so much, and Allah Hafiz.